In this video, we're going to look at bond typing a little bit, and I'm hoping again that this is familiar to you. Electronegativity is definitely something that we can use to rationalize bond type. And you may have heard of these three different categories of bonds: ionic, polar covalent, and nonpolar covalent. Think about bond type as a degree of sharing. And that's where this whole electronegativity piece comes into play. In an ionic bond, there is no sharing whatsoever. The electron is completely transferred. In an ionic bond, you've got atoms with very different electronegativities. One that's very high, like a fluorine, oxygen, nitrogen, an atom that really wants to steal an electron, and another atom that's got a really low electronegativity, and in fact, he'd like to give them away. So that's a match made in heaven. So when I think about an ionic bond, this could be like, maybe sodium fluoride. I think of a complete transfer of electrons, very different electronegativity values. Polar covalent obviously involves sharing electrons. That's the whole covalent bonding part, right? But polar means like opposite ends. In a polar covalent bond, the electrons are not shared equally. This is very common. You've got one atom with a larger electronegativity than the other. Now, they're both sharing the electrons. They both need to share in order to get a full stable octet, like hydrogen and fluorine. But they don't have to share equally. Hydrogen and fluorine have very different electronegativity values. Fluorine's is obviously higher, so the electrons will be held closer to the fluorine atom. And so with this red color, obviously your study guide doesn't have the red color, it's supposed to show a region of high electron concentration. Often you'll see this noted with a symbol that looks kind of like that. It's like this little squiggly Greek symbol, and then a negative. That means partially negative. That indicates that the electrons are held closer to the fluorine side of the molecule because fluorine has a higher electronegativity. That leaves hydrogen partially positive. Now it's a little different than sodium fluoride. In sodium fluoride, the sodium would just have like a +1 and fluorine is -1. There's a total transfer of the electrons. We're not transferring, like hydrogen can't just give it away. He needs 2 electrons to fill his first energy level, 1s orbital. But poor hydrogen, those 2 electrons are just held much closer to the fluorine. And then obviously nonpolar covalent would involve equal sharing of electrons. So the best example is like a diatomic molecule, F2, something like that, where the electrons are shared perfectly. The electronegativity values are essentially the same. Now you could look at a chart like this that lists exact electronegativity ratings, and sometimes they'll do this in first year chem where they'll have you determine bond type by kind of like subtracting electronegativity values, and then they'll say like if the difference falls in this category it's ionic, if it's in this category it's whatever. Caution, you don't want to do that on the AP test because it doesn't work if you don't know the electronegativity values, right? And you're probably not going to be given a chart like this with exact electronegativity ratings. Now I would obviously know that, like fluorine has the highest, and next would be like oxygen and nitrogen, and like chlorine, those are all the highest electronegativities, and the lowest are down toward the opposite corner. Francium, cesium, all those big guys. I would know the trend in electronegativity, and I would use that to predict bond type. I wouldn't try to memorize anything about like subtracting electronegativity values. I've seen people do that in the past. It's not wrong, but you're not going to get exact electronegativities on the AP test. Instead, I would know this. This first thing, I'm not even going to think electronegativities. I know it's ionic. Ionic compounds are always metal, nonmetal. And man, people forget that all the time. That's the easiest way to identify an ionic compound, metal, nonmetal. The metal is usually the atom that wants to donate electrons, and the nonmetal is the atom that would like to gain electrons. I mean, just looking at the periodic table and their electron structure, the amount of valence electrons you'd have, it makes sense. Oh yeah, like once I get over to the nonmetals, like the nitrogen, oxygen, fluorine, halogen families, that's where the outermost shell has like 5, 6, 7 valence electrons. Those are the elements that are going to gain the electrons. The first couple groups, and even throughout the transition metals, they may only have like 1, 2, 3 valence electrons. They're more willing to lose those electrons. So easy, ionic, metal, nonmetal. Second one, piece of cake, right? Nonpolar covalent. Say it, nonpolar covalent, NPC. Number one, I know it's covalent because covalents are all nonmetals. Oxygen and oxygen are both nonmetals. Nonpolar because it's the same stinking atom. So of course they're going to share electrons the same. Now, they're probably not going to give you something like this. Look how tricky this could be. Hydrogen and phosphorus actually have the same electronegativity, 2.1. Do you think they're going to give you like a phosphorus hydrogen compound? No, they're not going to do that. They don't expect that you know the exact electronegativity values of all the elements on the periodic table. That'd be crazy. So for example, if I see NH3, nitrogen bonded to hydrogen, I know that's polar covalent, PC. And in fact, I could tell you this, that in a bond, in a nitrogen-hydrogen bond, and obviously like there would be 3 of them, and then a lone pair on top, the electrons in that bond will be held closer to the nitrogen. The nitrogen is going to be partially negative, and all the little hydrogens will be partially positive. I'm not basing that on any kind of exact electronegativity value. I'm basing it on the position on the periodic table. These guys are the highest electronegative elements on the entire periodic table. So I know that nitrogen is going to have a higher electronegativity than hydrogen. The electrons will be held closer to the nitrogen. Polar covalent. Sharing, they're non-metals, so it's covalent, but not sharing equally. Because I know I've got little baby hydrogen bonded with one of the most electronegative elements on the periodic table. Same thing with water. Man, I would know water has polar covalent bonds. And I would know that in a water molecule, let's draw it to the true 3-dimensional shape, bent, just for kicks. I would know that oxygen has a higher electronegativity. Oxygen carries that partial negative, and then each of the hydrogens are partially positive. An oxygen-hydrogen bond is polar. They're sharing electrons, but not equally. Oxygen has a way higher electronegativity than hydrogen. So don't make this bond typing more than it needs to be. It's not meant to be something really crazy that you have to memorize. Ionics, metal, nonmetal. Covalents, all nonmetals. The best example of a nonpolar covalent, diatomics. Most likely anything else is probably polar covalent because they're not going to give you something super tricky like the phosphorus hydrogen or tricky carbon sulfur where they actually have very similar electronegativities. They're not going to ask you for one like that. These are really good examples of structures where I can just look at basic trends on the periodic table and predict how those electrons are being shared.